Let's discuss convolutions. Some people say a convolution is just a dense, and other people say a dense is just a convolution. So let's see if we can get to the bottom of this. Let's head over to the practice page and make some theoretical image data. We'll just do 28 pixels wide, 28 pixels tall, and black and white data, so one channel. And to keep things simple, we'll just do 64 here. Now, what we're going to have to do is to directly compare a dense and a convolution. They have to operate on the same amount of data. And the easiest way to make that happen is to either operate one pixel at a time or operate on all the pixels at once. So let's just go ahead and start with all the pixels at once. So let's make our filter size the entire image. So this is 28 pixels wide, 28 pixels tall. And I think I can leave this blank, but I'm just going to go and put one there. And then we have to match the target dimension. So we just have to flatten the data after this. And let's look at that. That's 50,000 parameters. Okay, now let's try and do a dense. To do a dense, we just do the reverse, actually. We first flatten the data because dense operates on the last dimension. So we need to get all the data into the last dimension. Then let's do our dense, linear, build that. And again, 50,000 parameters. So in this case, when we operate on all the data with either a convolution or dense, we got the same parameter number. So operating on a pixel at a time, this is known as a one-by-one convolution. And I think most people realize this is literally a dense because everyone knows that a dense operates on the last dimension, and a one-by-one convolution is simply transforming the final dimension. So I think most people recognize that this is equivalent to a dense. So this time we're going to make the filter size 1 by 1 pixel, and again, our stride is 1. This time, however, we have to, instead of flattening, we need to do a global average. We have to get all the, because we have 64 filters, so we need to get the average of all those 64. Okay, and we get 128 parameters this time. So now let's see if we can attempt to do the equivalent dense. We'll go ahead and do a dense here. Any activation will do. And again, 128 parameters. Okay, so that was image data. Let's say we had some data that a dense would normally use. For example, let's say we had 10 features, and let's say we were doing a regression task. Now, a dense would be pretty simple. We would just do this. We would go to 1 unit, and we're done. And we have 11 parameters. Okay, what if I wanted to do a convolution on this data? I would first have to reshape, because convolutions expect higher shapes than just one dimension, one tensor here, rank 1 tensor. So I have to reshape it. I'm just going to add 1 step, and then we'll do our conv1d. We'll do a 1 by 1 convolution with 1 filter because we did a dense to 1. And I forgot that we need to now, because we still have that extra dimension, I just need to flatten the data. There we go. And there we go, 11 parameters again. So we saw that when we had image data, we were able to do a dense that matched the convolution. And when we have just a feature vector, which we would expect to do dense operations on, we were able to do a convolution that matched the dense. So clearly, a dense and a convolution are the exact same operation. So then what's the difference? Well, a convolution is a dense that is applied to a portion of the data. that lets you do the same exact dense operation multiple times on the data, scanning for features. And why would you want to do that? You would only want to do that if your data had some sort of structure to it, because you're mixing the local features with each other. And it doesn't make sense to do that unless your data has order to it. For example, images or DNA sequences. And in the literature, you'll see a lot of people claim to have done a convolution because they use a convolutional layer, but they just did a convolution on all their data, and their data has no structure to it. So it's kind of a misnomer to use a convolutional layer and claim you're doing a convolution when you could have just done a dense on all your data. So hopefully we cleared things up there. So when you see convolution, just think, I'm just doing a dense to a segment of the data. Okay, thank you.